All right, our next topic in Unit 1 is vectors. It's also Chapter 3 in our book. But vectors is really the basis of this physics class. We will use vectors all year long. So what is a vector? A vector is a quantity where magnitude and direction are known, as opposed to a scalar, which is a quantity where magnitude is only known. So scalar examples would be like saying my house is 5 miles away. Okay, that's a scalar. It's just a value. The temperature in this room is 23 degrees Celsius. Just a value. We call that the magnitude, the amount. However, the vector has that magnitude but also a direction. So I could say my house is 5 miles away to the east. As soon as I put that direction on there, now it's a vector. Or I could say my displacement was 6 meters northeast. My acceleration is 8 meters per second squared at 15 degrees. So long as there's a direction associated with your value, with your magnitude, it's a vector. Notation, sometimes we'll leave this off, but if we're writing out a variable like, acceleration was a equals 8 meters per second squared, usually put this little vector hat on it. It might be bold in the textbook, but that's vector notation. So since vectors have directions, we can, of course, graphically represent them. We can sketch them out. So a few things we need to know. We need to know our regular Cartesian coordinate system, and then also how compass directions relate to that. So, we've got east, north, west, south, going around in a circle the way you would for your Cartesian coordinate system. But we do need to know what angles those are as well. So east, we say is 0 degrees, or that could be a full 360. North would be 90. You can keep going. West would be 180 degrees. South would be 270. So that's how the compass directions correspond to our Cartesian system. And when we draw a vector, we draw like an arrow, pointing in the given direction. So this example right here was 8 meters per second due east. All right, so it should have a correct size if you have some sort of scale on there and the correct direction. And notice this was meters per second. It doesn't just have to be a distance. We'll have vectors that are forces, vectors that are momenta. So it doesn't just have to be a distance. The unit could be anything. We would still graphically represent it the same way. All right, so just another example. Let's say I wanted to draw 12 meters per second squared at 45 degrees. All right, so we know, there's 0, there's 90, 45 be right smack in the middle. For most of this course, when we draw a vector, we just approximate where the angle is. But for a few, we will get out a protractor and actually sketch, exactly where 45 degrees is. If I were to draw another acceleration of, let's say, 6 meters per second squared somewhere on here, I would need to make it half this length. We do want to try to keep things to scale. All right, so vectors can be placed anywhere. I don't have to start at the origin. We usually start our first vector at the origin. For example, let's say you have a boat in a river and you have the velocity from somebody rowing, but there's also a current velocity, maybe at an angle. We can find out the net or overall velocity of the boat. Okay, so next slide. Which of these show the same vector? Is it A, is it B, or is it C? Well, there's something that's all the same about A. There's something that's all the same about B. But the answer is C. These have all the same magnitude, they're all the same size, and they're all pointing in the same direction. Yeah, they all started at different places, but they are all pointing at the same angle. A, they all have the same direction. B, they all have the same magnitude. They are the same size. But C really is the same vector, same magnitude and direction. And if you're a substitute playing this video, feel free to pause if I'm moving too fast. Okay, so again, ways to represent directions. 3 general systems used: the Cartesian coordinate system, compass directions, and then just sort of relative to a horizontal or vertical, which we'll see quite a few times in problems. So Cartesian system, compass directions. Okay, so let me just sketch out these. So 135 degrees, and you can subtract from 180 or 135 minus 90. That is going to be 45 degrees, sort of in quadrant 2 here. Remember your quadrants as well. Quadrant 1, quadrant 2, 3, and 4 going counterclockwise. 5 meters at 135 degrees, okay. Okay. So I can draw that. 5 meters at 25 degrees east of north. Okay, so directions based off of compass directions. When you have something of something, start at the second word, so east of north. So sort of point your pencil north, and you want to go east of that, so move towards the east. So from north, I need to move 25 degrees towards the east. So start at the second word. And that's really where my 25 degrees would be. Okay, you can also have the angle just relative to a vertical or a horizontal. When we do projectile motion, they'll often just say, whatever angle with the ground. So if you had 10 meters at 25 degrees above the horizontal, well, that could be this way, which we'd probably pick 25 degrees above the horizontal. But realize the horizontal extends over here, so it could also technically be 155 degrees. So just read the problem for specifics. It should hopefully be obvious which way to point that vector. All right, so a quick few to sketch. Why don't you guys take a second and try to sketch these out. Again, if you're subbing, I want to pause here, and then I'll come back and sketch them. Okay, so I just drew a few sets of axes here, but 10 meters at 10 degrees above the horizontal. Again, that was just like the one on the slide before. You would probably point it that way. And we're just sketching here, but still try to make your angles, somewhat close. You know where 45 degrees is, so don't make it more than that if it's only 10 degrees. But technically this one could go the other way. Okay, so I could have gone left or right. Those should be the same size. Next one, 10 meters at 60 degrees west of north. 60 degrees west of north. Okay, so start at the second word. There's north, and move towards the west. So 60 degrees from the north towards the west. So that would look like that. 3, 10 meters southeast. If it says, directly southeast, northwest, something like that, there's no angle in here. That does mean exactly in the middle of south and east. So that'd be 45 degrees, sort of in between south and east. So east is right, south is down. So right smack in the middle there. And last one, 10 meters at 30 degrees east of south. Okay, start at the second word, south, move towards the east. So 30 degrees east of south. So something like that. Next. Okay, so now vector addition. We can draw single vectors just fine, but now how do I add them? And it's not necessarily just adding the magnitudes, which hopefully will be obvious with this example. Let's say I'm trying to, row my little boat across a river, and I'm rowing at, 2 meters per second straight across, but the current is pushing me at 4 meters per second downstream. Okay, those things are perpendicular. I'm going across current's pushing me downstream, you know, that net, that overall that I'm doing, I would not say is 2 plus 4. I'm not going a total of 6 meters per second. Now, if I was going with the river, and the river's pushing me at 4 meters per second, and I'm rowing at 2 meters per second, absolutely, we could add them up. And we get the same answer using vector addition as well. So, adding vectors. First, just draw one vector. Next, and this little step I make up, I think it helps, draw sort of mini coordinates on top of that vector head. And then off of those little mini coordinates, just draw the next vector. You'll probably get a point where you can skip that step, but it's nice starting out. And then you can draw your answer, which is called the resultant. And that is tail of the first to head of the last. So you get the hang of these steps as we do a few example problems. All right, so let's start out with it. East and north problem. All right, and just sort of planning ahead, you know, east and north, as far as saving paper, you know, I only really need quadrant 1. And I'm still just sort of sketching here. I will try to make things to scale as much as possible, but step 1, draw one of your given vectors. So it does not matter if I draw A or B first. That should be clear. But I'll draw vector A, 10 meters east. Okay. So just an arrow pointing to the east. Again, this step's maybe a little irrelevant for this problem, but I do like little mini coordinates, like a little x and y axis right here. And so off of that little pink mini coordinate system, I'm going to draw the next vector, 5 meters north. So ignore everything you've drawn already. Pretend we're just starting at little pink coordinate system. And since I'm trying to make this to scale, it should be half as big as the 10 that I drew. And so now I've added these vectors. The answer is the resultant, which is tail of the first to head of the last. Okay, remember the head of the vector is where the arrow is. So tail of the first to the head of the last, so pointed towards the head of the last. And we'll call that the R, the resultant. Now, the resultant is a vector as well. You know, it's got a magnitude, it's got a certain length here, and it's got a direction, so I need to explain what those are. I need to be able to tell somebody else what my answer is so they can reproduce this drawing of this blue vector, even without the green ones. Okay, so magnitude, this is nicely a right triangle, so I can do Pythagorean theorem there. So we know r squared equals 10 squared plus 5 squared, so square root of 125, 11.2. Okay, same unit, meters. At, you can't just stop there. Do not stop without the angle. So what angle am I even talking about? I need an angle where somebody else, again, could reproduce this blue vector. So I need to tell them this angle, you know, with 0 for my original coordinate system. All right, well, thank goodness we've studied our trig, and usually we'll be using inverse tan. Inverse tan, because we've got the opposite side, we've got the adjacent side, it's a right triangle, very conveniently a right triangle. So tangent is opposite over adjacent, but I want to do inverse tangent. To get my angle, making sure you're in degrees. And we get 26.6 degrees. So that is my final answer. My final answer is a vector. It's got a magnitude. It's got a direction. All right, one more example. In fact, even easier. This is just west and east. Draw one vector. Does not matter which. I'll go west first. Again, you can throw on the little mini coordinates if you want. Maybe not relevant in this particular problem. From the head of that vector, again, we add vectors head to tail, draw the next vector. So 10 meters per second back to the east. Which of course means I don't end up where I start, but the answer is tail of the first to head of the last. So most people could have told you the answer was 2 right off the bat. But do make sure you get the direction right. I mean, there was more velocity to the west. So it should make sense west wins out, but if we drew our result correctly from the tail of the first to the head of the last, it points west. So west is our direction. Okay, so that was nice and easy, and honestly that was something we did in honors physical science in 9th grade if you took the honors class, but the big question is, what if vectors are not at right angles, or what if they're just not in a line, like that last example was? So there's, of course, a way to solve vector addition problems when vectors aren't at right angles, but first do check to make sure they are or not. You know, check if they're at right angles or check if they're in a line. That'll make your life a lot easier if they are. How do you know if angles are right angles? Well, just subtract the angles you're given. You know, if they're 90 or 270 degrees different, then you have a right angle. If it's 180 degrees different or 0 degrees different, then they're in the same line. And it would be like the problem we just did, where it's just back and forth, real easy math. But if they're not at right angles, we have first an approximate technique, which again, some of you may have done in 9th grade, and that's just using a ruler and a protractor. You know, we'll sketch the vectors to scale with the ruler, we'll draw out a correct angle with the protractor, we'll still sketch our resultant, and we'll determine the magnitude and direction sort of based off our scale with the ruler and with our protractor. Okay, so at this point, if you're a substitute, make sure everyone has a ruler and a protractor. So we can all try to do this one together. And it might help if you do this on a separate sheet of paper. If you printed out these notes, I don't know if you can fit them in a little slide. Just depends on how big your notes are, I guess. But probably do this on a separate sheet of paper. So if I want to add these graphically, like I said, first check, just make sure these angles aren't 90 degrees apart and we don't have a right triangle situation. So you got 130 and 15 degrees, you know. Okay, that's definitely not 90 degrees or 270, so sadly I'm not going to have a right triangle situation. So, since I'm going to try to do this neatly, and with my ruler and protractor, use your ruler, and if you got line paper, use the lines to draw the axes. Although, again, it might be nice to just make a very quick sketch so you kind of know where on your paper to start. Sometimes in 9th grade we always had the issue we went off our paper. Well, 15 degrees, let's see, that's going to be a vector in the first quadrant, something like that. From there, I got to do 130 degrees. Remember, you know, little mini coordinates. 130 degrees is in the second quadrant. You know, 5 is definitely shorter than 10. So that's sort of my picture, where the black line will be my answer. So I really only need the first quadrant to work with. So you don't have to put the origin in the middle of your paper. I'm going to kind of put it down here and maximize my space. Let's see if I can make some nice straight lines. I say decent, you probably could square that up a little better than I can. All right, so I'm going to draw these out to scale, so I need a ruler, I need a protractor, and I've got to come up with a scale. And just keep note of whatever your scale is. You probably could just do a 1-to-1 scale with centimeters right now. And remember, there's about 30 centimeters in a ruler. So, every 1, 2, 3, that should be a centimeter. I know the rulers often say little mm for millimeters. But that's just the itty-bitty little marks. So, whatever set of numbers goes up to 30, that's your centimeters. So, start though by marking off your angle. I want to measure this vector at 15 degrees. So I need to mark off where 15 degrees was, or is. And you have 15 degrees labeled twice on your protractor. All right, please use your common sense that 15 degrees is in the first quadrant. I know there's a 15 degrees over here, but that's not really 15 degrees. Yeah, that'd be 15 degrees off of 180. Just put a dot. Put that little pinhole of your protractor on your origin and just put a dot where 15 degrees is. Get rid of that for a second. Then bring my ruler down. And now just aim your ruler at your dot. And already I'm going to be a little bit off because my axes aren't quite square there. Okay, so now I've got my ruler sort of lined up with my dot starting at 0. And I set my scale, 1 centimeter equals 1 meter. So I really want to draw all the way out to 10, just doing a 1-to-1 scale. Okay, I'll get rid of that for a second. Throw my little arrowhead on there. Okay, so I drew 1. And again, this is why this is an approximate technique. I'm not quite on the dot. I made it 15 degrees. But I should still be pretty close in the end. I like to draw little mini coordinates. Mini coordinates are still up, down, left, right. Do not draw it at this slant like that. I've seen that in 9th grade. Up, down, left, right. Little mini coordinate system. All right, and now you can ignore everything else you've drawn and just draw your next vector right here. So I need my protractor back. And I want to go to 130 degrees. Now 130 degrees is in the second quadrant. Again, ignore what you've already drawn. Don't think you have to end up over here because this was the second quadrant of the original coordinate system. We're only dealing with our little mini coordinate system, which again I haven't drawn super square. But based off this little pink coordinate system, 130 degrees, is the second quadrant. So make sure you pick this 130 degrees and not the 130 that goes off in the first quadrant. So your pinhole's right here on the head of your last vector. Just put a dot. Just a little mark at 130 degrees. Get your protractor out of there. Set your ruler back up. Now put your ruler again on the little pink mini coordinate system. Get your 0 right there. Rotate it around and line it up with your dot. So now when I draw out to 5, that should, hold on. There we go. I am just a little bit shy of my dot. The dot's just telling you which way to go. Don't think you need to draw and stop at that dot. So I have now added my 2 vectors. I've drawn them pretty well to scale. And now my result, my answer, is tail the first to head the last. I will try to do this with my ruler. And as long as you put 0 at your original origin, this will give you your magnitude right off the bat. Look looks like my magnitude is just shy of 9, although I think it really is supposed to be 9. So look at your ruler, measure that resultant. Mine's about 9. So I've got about 9 meters at, and I still need an angle. What angle? Not the angle between the black and the blue. All right, I need to tell somebody else how to draw that black resultant vector from my original coordinate system. So I really want to measure this whole angle. You know, tell somebody what it is based off of 0. So get your protractor back out. Put the pinhole back on the original origin, and then just, measure what it says. Again, I've got the choices of something between 130 and 140, and something between 50 and 40. So it's the first quadrant. It's got to be between 40 and 50. Can't be past 90 yet. So I'm going to say mine's maybe just shy of 45, 44 degrees. And that is how you add vectors graphically. And it doesn't just have to be 2 vectors. We could have added up 100 vectors like this. Final answer is still tail of the first to head of the very last. I think I've got the exact answer on here. Let me see. Okay, so that's what we got graphically. In a moment, we're going to actually solve for it mathematically and see how close we were. We should be pretty close. Okay, so how do you solve for vectors exactly when they're not at right angles or in a nice straight line? And that's called the components technique. We solve for the components of the vectors. So every vector can be thought of as a sum of other vectors. So kind of annoyingly, if we had to add 2 vectors like we just did, 10 meters at 15 degrees, 5 meters at 130 degrees, to get the exact right answer, instead of dealing with 2 vectors, we're going to turn those 2 vectors into 4 vectors. And those vectors are called the components. So every vector can be thought of as a sum of 2 components. Here's vector A, for example. The components make nice right angles, and that's why we draw them that way. This could be the resultant vector of, well, really many bajillion combinations of vectors. It could be the resultant of those 2. It could be the resultant of all of these vectors. Add them all up head to tail of the first to head of the last. Could be. But it could be the resultant of what we call the x component, which is basically just how far along the x-axis we go, how far right or left. Call that AX, and the sum of the y component. And the y component would just be how far up or down you go to make that vector. So again, we could think of vector A as the sum of AX plus AY. A little more work to turn one vector into 2, but when we have things at nice right angles like that, it makes our math a lot easier. So let's say we want to add vector A and vector B, as shown here, and get the resultant. I'm just going to sketch that idea first. So vector A looks like about 45 degrees, just up and to the left. Vector B looks like it's a little bit farther to the right, but up and right. Maybe something like that. And then I'll draw in black the answer. The result would be this. So that is the result. So instead of drawing vector A plus vector B to get the result, and you can leave this on your paper, I'm actually going to draw AX plus BX and AY and BY all added together. I'm going to turn those two vectors into 4. So if A plus B equals R, but A really equals AX plus AY, and B really equals BX plus BY, I can add all of those up to get the result. So as a sketch, do it red. AX is actually left. AY is up. BX is right. BY is up. So now let me draw all the components, and I should really end up with that same R result value. So I'm going to do x's together first. Usually we would combine the x's and combine the y's. So I'm going to add these two guys first. AX was left. Something like that. But then BX was right. So again, adding them off of each other from here, I'll draw the next. And look, I now end up right underneath sort of the x value of that resultant. All right, and then the y's. AY was up. Probably almost all the way to R. And BY was also up, just a little bit. So I still end up getting the same result value. So that's the idea of adding vectors that are not at right angles. Find the components, and we can numerically find what these values are. Then add up the x's, add up the y's, and make one last triangle. So again, the x and y components are always helpful because they make right angles. It is possible you have a vector that's already north, south, east, west, something like that. We would just say here that there is no x component. Say ax equals 0. Because you don't go left or right to make that vector. Ay just happens to equal a, 5 meters up. Okay, so let's go back to our problem we just did graphically and see if we can mathematically get the exact answer. Again, on the board I got 9 meters at 44 degrees, so let's see how close we are here. And I'm actually going to do it on a blank sheet here. You might need a little more room. But again, never a bad idea to just have a sketch of what you're kind of shooting for. A was 10 meters at 15 degrees, and B was 5 meters at 130. And so that's my result. So, in my mind, I'm expecting an answer, in the ballpark of 10 maybe, but definitely between 0 and 90 degrees. If I get something more than 90, I know I'm wrong, or most likely wrong based off my sketch. All right, so I want to add these mathematically. Just draw one vector by itself at a time. So here's vector A again. And now I draw the components. So I've got the x, sort of the right component, and the up component. But now I do need values. I need to know the actual length of AX and the actual length of AY. So this is where I need to be good at trig. And I'll erase this here in a second, but if I have this angle, and I know the hypotenuse, AX, the way I've drawn it, and again, it doesn't always mean AX is going to be the cosine function, but the way I've drawn it, AX is the adjacent side. Okay, so this is cosine. So cosine of 15 equals adjacent over hypotenuse. So just multiply cosine of 15 times 10. And I get AX equals, say, 9.66. Technically meters. AY, on the other hand, based off of this triangle that I've drawn, is the opposite side. So that would, of course, be sine of 15 AY over 10. You know, multiply 10 to the other side to get AY by itself. And I get 2.59. Okay, I'm going to clear that math, though. I'm going to erase. And those are my x and y components. Now I need to do the same thing for B, which was sort of up left here. I know it's at 130 degrees, but I am definitely not going to put 130 degrees in my triangle. So think about what that would need to be. This whole angle is 130. You know, the BX is sort of on the 180 line. Well, that little chunk there's got to be 50. Now, I should also note that that's just simply how I drew these components. You could have drawn BY first. You could have had the same B and gone up BY and over BX. Doesn't matter. You're still showing how much you go up. You're still showing how much you go left. But your angles would be different. If I drew it like this, my angle inside that triangle would have to be 30. Nope, 40. And that's just the 130 minus 90. Gets me 40 degrees right there. So you don't have to draw the triangles exactly the way I've drawn them. But realize if you draw them different, you might have a different angle in there. Okay, so the overall angle is 130, but in my triangle I've got 50 degrees. That's important. Don't plug in 130. Alright, back to my trig. BX is again going to be the adjacent side, so that's what I want to do. Cosine. Cosine of 50 equals BX over 5. So that would give me 3.2 meters. And then BY is going to be sine. So just sine of 50 times 5. And I get 3.83. All right, I'm going to erase that math. I'm trying to save a little room. Okay, so we've found the components. We actually have the numerical values for the components. Now we add them up. We still kind of add them like vectors. And before I add them up, I should take into account the difference between left and right and up and down. Anything that's left, we usually call negative. Anything that's down, we also call negative. So AX is right, AY is up, both positive. BY is up, positive, but BX is left. So I really should throw on a negative sign there. Now I'm going to get my overall X and Y values. So really that's the resultant's X value and the resultant's Y value. So the resultant X would be 9.66 plus negative 3.2. And our Y would be 2.59 plus 3.83. All right, so we get 6.46 and 6.42, hopefully. Yeah. So those are my resultants components. Still not my final answer, but now I can sketch that out from one last vector picture. And again, here was my original sketch. Here's the result I'm looking for. I now know the X value to that and the Y value to that. So there's R. Our X is 6.46. Our Y is 6.42. And I'll just get a little more room now. And the whole point of doing all that work was so that these would be at right angles. So I now can find R by doing Pythagorean theorem. And for me, since I remember what I got with my protractor ruler, I'm kind of hoping for an answer close to 9. Let's see, 6.46 squared plus 6.42 squared. Yes, 9.1. So 9.1 meters is the exact right magnitude. And now I just lastly need a direction. So I need that angle. So I have opposite and adjacent to this angle. So I need to do tangent, inverse tangent. And since those are essentially the same, it's going to be very, very close to 45. Yeah, 44.8. And the angle is usually what tells me how good you made your drawing when you use the graphical technique, because if your angle is way off, then I definitely know something went wrong. All right, so that is adding vectors by components. Quick recap, you have two given vectors, draw them separately, find the X and Y values of each, add up the X's, add up the Y's, and make a picture out of that. Draw a vector diagram out of the x and y values. Pay attention to negative signs though. If anything's down or left, it really should be a negative component. All right, and that concludes vectors.